In this video, we're going to go over how to solve second-order linear recurrences, and we'll show an example. So a second-order linear recurrence is going to have the form an equals some constant times an minus 1, so some constant times an minus 1 plus some other constant times an minus 2. And if we assume that the recurrence starts at a0, then this is for n greater than 1. And we'll explain the method for how to solve this. Let's just look at an example. Suppose that it's a sub n equals a sub n minus 1 plus 2 times a sub n minus 2. And we want to solve this. So we haven't specified any initial conditions. And we're going to get an infinite number of solutions to this. So it turns out that when you're solving something like this, it helps to first look for solutions of the form r to the n. So first, we'll find all numbers r not equal to 0, such that a sub n equals r to the n is a solution to the difference equation. So in this case, it helps to write a sub n minus a sub n minus 1 minus 2 times a sub n minus 2 equals 0, just to get 0 on one side. And now if a sub n equals r to the n, then we have r to the n minus, and then a sub n minus 1 is r to the n minus 1, and then minus 2 times a sub n minus 2 is r to the n minus 2 equals 0. And now we assume that r is not 0. Well, so we first factor r to the n minus 2 out, and so that's going to give you r squared minus r minus 2. So since r is not 0, we can divide both sides by r to the n minus 2 and get r squared minus r minus 2 equals 0. Now we can factor this. This is going to factor as r minus 2 times r plus 1 equals 0. And when you set each factor equal to 0, you get r equals 2 and r equals negative 1. So this shows that if a sub n equals r to the n is a solution, then r must be either 2 or negative 1. In fact, we can, if you think about it, this doesn't actually prove that 2 and negative 1 work, but if you just go back, this is if you use 2 to the n, negative 1 to the n, that's going to work. Okay, because these are all equivalent. Since r is not 0, these are all equivalent statements. So if r is 2 and negative 1, then you get that equation, and that equation, and that equation, and that equation, and that equation. That's what I'm trying to say. So 2 to the n and negative 1 to the n are going to work. You don't actually have to check that they work. So a sub n equals 2 to the n and a sub n equals negative 1 to the n are solutions to the recurrence. Okay, now it turns out that there is a fact that if you take any constant times 2 to the n plus any constant times negative 1 to the n, that is also a solution. So if you take c times to the n plus d times negative 1 to the n, that this is a solution to the recurrence for any constants c and d. By the way, the c and d are not the same as the c and d that I wrote above. Okay, let's check that in this case. So we need to check that a sub n is equal to a sub n minus 1 plus 2 times a sub n minus 2 using this expression for a sub n, right? Because to check that this is a solution to the recurrence, we need to plug it into the recurrence equation and check that it's true. So we're going to calculate the left side. Well, the left side, you don't need to calculate anything. It's just this. But we want to know if it's equal to the right side. So the right side is going to be c times 2 to the n minus 1 plus d times negative 1 to the n, because, n minus 1, and then plus 2 times a sub n minus 2, which is c2 to the n minus 2 plus 2 times d times negative 1 to the n minus 2. And let's see. Are these the same? Apparently they are. Oh yeah, because if you look at this, that's going, so if you look at these two terms added up, it's going to be c times 2 to the n minus 1. So c times 2 to the n minus 1 plus, and then 2 times 2 to the n minus 2 is 2 to the n minus 1. And then this is going to equal 2 times c times 2 to the n minus 1. Then you multiply it by the 2, so you get c times 2 to the n. Okay, so that matches the c times 2 to the n on the left. And now this one, that is going to give you I mean, one can check this just if n is even. So if n is even, and if n is odd, right, you break it into two different cases and check that you get the same thing. But I think there is a more clever way of doing this. Because if n is odd, then you just get, so n minus 1 is even, so you just get d plus 2d times negative 1 is negative d, and then that matches with the left side. And if n is even, then you get d times negative 1 plus 2 times d, which is equal to negative d plus 2d, which is d, and then that matches the left side again. So that works, but I think there's probably a cleverer way of doing this. Well, either way, in this example, we can see that it works. Okay, now the punchline is that it turns out that this is the only general solution. Okay, so fact, an equals 2 to the n, c times 2 to the n plus d times negative 1 to the n is the general solution to this recurrence. Okay, why is this? Because if we specify a sub 0 and a sub 1, that will determine C and D. So in other words, there's exactly one choice of C and D that will satisfy the recurrence once we specify the initial conditions. And when we specify the initial conditions, there can be at most one recurrence that works. So, right, because once you know what A0 and A1 are, you can use the recurrence to figure out A2 and A3 and A4 and so on. So now that once you find a solution, then you know that that must be the only solution. So that explains why in the case where we didn't specify the initial conditions, that we actually have found the general solution. Because if there were some other solution, then when we specify the initial conditions, that would give us some other solution to that recurrence. Okay. So this is the general solution. It's not just also a solution, this is the general solution. And so once we, so I just claimed that once you specify A0 and A1, you can solve for C and D. Let's just test it in this example. So suppose that in addition, we have A0 equals A1 equals 3. Well, in this case, so we know that AN equals C times 2 to the n plus D times negative 1 to the n is a solution. Can we find one where A0 and A1 is 3? Well, if A0 is 3, that tells us, substituting n equals 0, we get 3 equals C times 1 plus D times 1, so that's C plus D. And then substituting n equals 1, we get 3 equals 2C minus D. And can we solve for C and D? Yes, we can. We just add both equations and then get C equals 2. And then if C equals 2, we get D equals 1. And so the general solution is, the solution to this recurrence with the initial conditions A0 equals 3 and A1 equals 3 is 2 times 2 to the n, that's 2 to the n plus 1 times negative 1 to the n. So if we give A0 and A1 actual values, we say what they are, then we found a solution of the form C times 2 to the n plus D times negative 1 to the n. And again, that means that all initial value problems can be given using this form. Okay? This is if the roots are distinct in this equation. So in this case, we had r squared minus r minus 2. These have distinct roots. And then that gave us this. So you can use this for any linear recurrence that's second order that looks like this. A sub n equals C A sub n minus 1 plus D A sub n minus 2. And solve it as, well, this is how you do it if the roots are distinct. If the roots are not distinct, then it gets a bit more complicated. And we'll talk about that in a different video.